Alright, so topic number one, which you need to know for your paper one exam, is going to be energy. So the first thing we want to talk about in terms of energy is the idea of energy systems. So systems here, we've defined it very nicely for you. It's an object or group of objects. So that's a nice highlight. So it can be anything. So if you were to take a ball, this would be a system. If you were to take that ball and put it in a box, this will still be a system. Okay, so these are both examples of systems. And that's how we understand energy. A few situations which include systems which you might want to be familiar with is the idea of throwing a ball upwards. And actually here we can introduce this concept of conservation of energy. And basically what that means is that the energy or the total energy at the beginning is going to be equal to the total energy at the end. So if we were to take this system and we say we're going to give this ball 10 joules of energy at the beginning, that means that any time we come back to this system, as long as no energy leaves the system, then there's going to be 10 joules of energy at the end as well. So for example, when the ball is down at the bottom here versus when the ball is all the way at the top here, there's still going to be 10 joules of energy within the system. Now we come to this concept of energy transfers. So we said the total energy has to be the same. So this is quite a key idea that we're looking at total energies here. We're not looking at the specific type of energy, and that's because energy can take lots of different forms. So for example, over here, we said we gave the ball 10 joules of energy, right? So what kind of energy was that? Well, if we're going to throw the ball upwards and initially the ball is not moving, then essentially we're giving it kinetic energy. So whenever you cause something to move or speed up, you've given it kinetic energy. Now, when the ball reaches a certain height and you raised it above, let's say 10 meters, that means you've given the ball gravitational potential energy. Now, these are two different types of energies, and the idea is that at the beginning there was 10 joules of kinetic energy. Remember, that's what we said. And we know from conservation of energy, there has to be 10 joules of energy at any point in the system, okay? So that means that even when the ball is at the top over here, there still needs to be 10 joules total energy. So if the ball is not moving and there's no kinetic energy, then there has to be 10 joules of gravitational potential energy as well. So let's look at this in a little bit more detail. If you were to take this ball over here, and we said again, we're going to give it 10 joules of kinetic energy, and then we throw up in the air, and at some point over here, now at this point, we're going to say that it's got kinetic energy because the ball is still moving, and it's also got some gravitational potential energy. And so the idea is if you were to add both of these together, they would have to equal 10 joules. Now individually, they could be different. You could have 5 joules of kinetic energy and 5 joules of gravitational potential energy, or perhaps 6 joules of kinetic energy and 4 joules of gravitational potential energy. That's completely fine as long as the total energy is 10 joules. That means energy can be conserved. And you can see how this can be useful. If you can work out the energy of one, for example, kinetic energy, we'd also be able to tell that the gravitational potential energy would just be the total energy minus the kinetic energy, where we can use it in calculations. So that's one example, throwing a ball upwards, and we'll look into using calculations a bit more in a second, but first we'll go through some more situations we need to be aware of. So a second one is boiling water in a kettle. So this is our kettle, and kettles, as you know, will have a base over here, and that will be connected to some electric plug over here, which you won't draw. I'll just draw a little lightning over here to signify that this is electricity. And so the idea here is, again, we have an energy transfer. So over here, we've got electrical energy. And when you boil the kettle, the idea is you want to put heat into over here, heat into the water in the kettle. And so you're increasing the heat energy, or you can also call it the thermal, and both of those are acceptable. So that's another example situation where you have an energy transfer going on. Now let's take a look at burning coal. So for example, over here, you might have a block of coal. I'm just going to label it coal. And if you light a fire underneath this coal, then the idea is you start to burn this coal. And when you burn this coal, it can release energy, okay? And so this coal, we say it has a store of chemical energy, or you can also say chemical potential energy. And it's potential energy because it's kind of locked up, and you only can get it out once you actually burn the coal. Okay, so that's another example we should be aware of. The next one we're going to look at is a car using its brakes to slow down. So if we take a car over here, and let's say this car is going really, really quick, and let's say it's going at a speed of 200 meters per second. And then we suddenly slam onto the brakes, and now our car stops moving. In this situation, this car has now stopped moving, and it's going at 0 meters per second because it's not moving anymore. Now what's happened is over here, we've got lots and lots of kinetic energy because the car's going very, very quick. Remember, when we increase the speed of something, we give it kinetic energy. So to get this speed, the car has to have been given a lot of kinetic energy. So when it's at this speed, it's got loads of kinetic energy. Then you slam the brakes, it hits to 0 meters per second, it stops moving. And all of a sudden, all of that kinetic energy has gone. But where has it gone? Because over here, we mentioned conservation of energy. And that is, again, the idea, the total energy has to be the same at all points. So energy can't be created or destroyed. So even though we've lost the kinetic energy because we've gone from 200 meters per second to 0 meters per second, that energy has to have gone somewhere. And so the idea is when you slam onto your brakes, you actually end up generating a lot of friction, and as a result, you increase the thermal energy in the brakes. And that's basically where all that kinetic energy has gone. So you have some amount of kinetic energy linked to the speed, and when that speed decreases, that energy is transferred to thermal energy in the brakes, or thermal energy between the wheels of the car and the road. Okay? And we can also take a look at dropping an object which doesn't bounce. So for example, if you take a ball over here and it hits this floor over here, and once it gets to this stage, it doesn't bounce, right? The ball just stays still. Okay, so this is the second stage, whereas the ball is just staying still. And so what happens to the energy over here? So when the ball is up here, because there's a certain height that has been lifted up, because h, so it's got some gravitational potential energy. And as the ball starts to fall down, that means it's increasing its speed. It's got some kinetic energy, okay? You have some kinetic energy as the ball starts to fall. Now when it hits over here, the ball doesn't bounce. So all of a sudden, the kinetic energy has gone. The gravitational potential energy has decreased to 0 because now it doesn't have any height. It's not raised above this ground any height. And therefore, where has all this energy gone that it started off with? So the idea here, we have this concept of energy dissipation, where the energy from the kinetic energy and the gravitational potential energy is basically dissipated into the surroundings. And you can also say you increase the internal energy of the objects. Okay, so in this system, we've got the ball and the floor over here. And so on both of these, you actually end up increasing the internal energy. Okay, so the important thing to remember throughout all of these situations is that the total energy has to be conserved. Okay, so when we say that the energy has gone, that means it has to have been transferred to some other different types of energy. So here you can see gone into the surroundings, usually as thermal energy, or it's gone into internal energy. You could also have sound energy when it hits this ground as well. The next one we're going to look at is a ball accelerating with a constant force. So if you have some acceleration over here, immediately you should be linking the fact that you're increasing the speed. The speed is going up, and therefore the kinetic energy is increasing. Okay, and so you have an increasing kinetic energy. But the idea is that what we're interested in is actually what's causing this ball to speed up. So if this ball is speeding up along the ground, then there needs to be some force acting on the ball. And so the idea is if you have a constant force acting on this ball and you move it this distance, let's say d, then there is also some you are transferring energy. Okay, this is what we call doing work. So doing work is basically where you transfer energy, but you have this force involved. So whenever you have a force, if you multiply these together, and we'll look into the formulas in a bit more detail later, but when you multiply the force and the distance together, then you get the work done. And that basically is the same thing as the energy that you transfer to this ball over here. And as we mentioned, that energy has to go somewhere, so usually it'll be transferred into kinetic energy, perhaps some thermal energy to overcome the friction over here, or anything else. But again, the idea is energy is conserved the whole time. Okay, so we've introduced basically the concept of energy and transferring energy, and to actually be able to solve these and work with numbers themselves, you kind of alluded to it over here, but you need to know the actual formulas. So let's look at some of the formulas which you want to know. So actually, let's use the situations we've already drawn out. So over here, we talked about kinetic energy, and kinetic energy we should know is equal to a half multiplied by the mass multiplied by v squared. They use v here because technically it's velocity, but you can just use speed. Okay, in this case, they would be interchangeable. So it's half times the mass times by the speed squared. Okay, so if this is moving at a speed of 10 meters per second, for example, and it weighs 2 kilograms, then you should be able to put these numbers into your formula to work out what the kinetic energy would be. Over here, we also mentioned the gravitational potential energy, and that is going to be equal to the mass multiplied by the gravitational field strength multiplied by the height. So when we said here, the ball was lifted at a height of 10 meters, for example, and gravitational field strength generally on Earth tends to be 9.8 newtons per kilogram. And generally, they'll give you this in your exam, but just in case they don't, that's what it is. And so you would just do, if again, the mass was 2 kilograms, then you can see you can plug all of those in to get the gravitational potential energy. And remember, you could use both of these formulas together to work out the total energy. Okay. Next, we talked about electrical energy, which we'll actually come back to in a second because we'll define it here, but actually this does go into the topic of electricity, where power equals the current multiplied by the voltage, and therefore the energy is equal to the power multiplied by the time. And so if you multiply both of those together, then essentially you would get the energy. Okay, but we'll look into that more detail later. The next one then we talked about is thermal energy, and we'll define thermal energy over here. So thermal energy, when you increase the thermal energy of a fluid, basically you can use this formula that the change in energy is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature and we'll call it theta in this case. So theta just means a change in temperature. And so if you haven't seen this formula before, essentially you just take the mass of the liquid. So let's say you've got 1 kilogram of water in your jug, the specific heat capacity of the liquid. So that changes from liquid to liquid. So water, let's just call this liquid X, whatever liquid it is. We'll just say it's 300 at the minute. And that's the specific heat capacity. And that will be given to you normally, or you can work it out. You don't need to memorize it. And then delta theta is the energy change. So if you've gone from delta theta is a temperature change. So if you've gone from a temperature of 20 degrees Celsius to 100 degrees Celsius, if you're boiling water, for example, that means the energy change would be 80 degrees Celsius. And then when you multiply all of those together, you'll get the total energy change. I think I said energy change here. So this is the temperature change. So the total energy change would just be when you multiply all of those together, and you should get how much energy you've actually transferred into that liquid. Okay. Coal, we can talk about stores of chemical energy. We don't need to know how to work that out. That's fine. And then here, this situation again was just kinetic energy and thermal energy. In this case, you don't have a liquid going on, so you wouldn't be able to use this formula over here. But you could still use the formula for kinetic energy to work out how much thermal energy you've transferred. And in this case, again, surroundings and internal energy, we don't need to know how to work that out. But again, we've got gravitational potential energy and kinetic energy. So using the formulas, we should be able to work those out. And the last one here was the work done. So the work done is going to be equal to the force multiplied by the distance in this scenario. Again, where you're pushing a ball with a constant force through a distance d, if you multiply that force by that distance, you will get the work done or the energy transferred by that force. Okay, so that is how you calculate energy. There is one more which we didn't discuss, which you do also need to know, and that is elastic potential energy. And as the name suggests, basically it's whenever you have some kind of elastic, whenever you basically stretch something or compress something, you also give it some potential energy. And so the easy way to look at this is with a spring. So let's say you have a spring over here, and when you don't touch it, you don't stretch it, or you don't compress it, as a length of 10 meters. Then you take your spring and you decide you're going to stretch it all the way out to 15 meters. Now, in order to do that, you've also had to put some force in. And therefore, we know that when you put force in and it travels through a distance, that means there is some work done. So you've done work on the spring. So where has that energy gone? Well, it's gone into elastic potential energy in the spring. And the formula for this one is similar to ones we've seen before, where the elastic potential energy, we'll call it E, little e, is equal to half multiplied by K multiplied by E squared. Okay, so let's define these. So K is basically your spring constant, and this tells you how stiff your spring is. Okay, so different springs will have different springs constants, and the higher this is, that basically means the more stiff the spring is. Now, E is your extension. And so over here, basically, we had two measurements. The first measurement we had was this length of 10 meters over here. And then we had 15 meters over here. And so the idea is that the extension is the difference between these two. So this is the unstretched length, remember. This is how much the spring is after we stretched it. So the extension is just basically 10 minus 5 is 5 meters. We stretched it 5 meters from its unstretched length. So that's what we call the extension. And then again, you can see usually your spring constant will be given to you. So let's say it's just 15 over here. And so if you can just plug these in, you'll be able to work out the elastic potential energy. And the spring constant, you should know, has a unit of newtons per meter. Okay, so it's useful to know that as well. Extension is meters normally as well. So this could be, as we said in these questionnaires, meters is given to you. Right. Okay, so that's the last formula that we need to know. We've covered all the formulas now. And so now we can move on to power. And so with power, it's essentially, we've kind of already touched on it again. It's the energy transferred divided by the time it takes to actually transfer that energy. So basically, you can think of it as the rate of transferring energy. And so let's take a look at an example, because that's the easiest way to look at this. So let's say you have a ball over here and it weighs 10 kilograms and you lift it a height of 9 meters, and this is the new ball over here. Now straight away, when I'm telling you I'm lifting it a height, you should be thinking, right, you're gaining gravitational potential energy. And if you do remember, the formula for that was mgh, or mass multiplied by the gravitational field strength multiplied by the height. So we can actually go ahead and work out how much gravitational potential energy we transferred to the ball over here. So let's call it EP is equal to the mass, which was 10 kilograms, multiplied by g. Now g is the gravitational field strength, and normally on Earth be 9.8 newtons per kilogram, and usually they'll give that to you anyway, and then multiplied by the height, which is 9 meters. And so if you go ahead, put that in your calculator, you'll work out the elastic potential energy. So I'll just go ahead and do that. Okay, so I got 882, and the units, is joules. Okay, units of energy are joules. So we know we've got 882 joules of energy. That's great. So how do we connect that with the power? Well, we know the power is equal to the energy transferred divided by the time. So let's actually work out the power. And to do that, we obviously need the time. So let's say I did this in 20 seconds. So I will do 882 divided by 20. And if you work that out, and I'll try and do it in my head, but I think you should get 44.1. Okay, so the power is actually 44.1 watts. Okay, so the units for power is watts. You can also call it joules per second. That's the same thing. Because you can see over here, this was in joules and the time was in seconds. So joules per second or watts is the same thing. And this is actually an interesting calculation to do because we can actually see what happens to the power when we change the time. So now let's say we change the time to 40 seconds. So it takes twice as long. So again, we have the same energy transferred, but we take twice as long to do it. And if you work out the power rating now, you should find that you should get 22.05 watts, if I did that correctly. And so basically what's happened is you have exactly half the power rating, despite the fact that the energy transferred is the same. Because you took twice as long to do it, your power rating is half. Okay, so that's essentially the link between energy transferred and power. Now, power basically leads quite nicely on to the next thing we need to talk about, which is efficiency. Now, efficiency, basically, we can define it as follows. It's the useful energy divided by the total energy. And a lot of the time, we actually multiply this by 100% because we will usually give this in a percentage. Or a lot of the time, we give this in a percentage. And actually, we could also write, instead of energy, we could replace that with power. It's the useful power over the total power. Good thing to remember is that this is usually input. Sorry, this is output. And over here, total energy is input. And the same thing over here. Oh, wrong way around. Okay, so hopefully that just gives some context. And so let's again look at an example. That's the best way to look at things. So if we have toy car over here. So it's a toy car. So we're just going to push it along with a force from our hands. And so we're going to put a force F and we're going to move this car a distance D. Okay, so we have our car now over here. Perfect. Now immediately you should be screaming out the formula we're going to use to work out the energy. So the energy transferred over here is going to be equal to force multiplied by distance. Now that's great. Now the thing is, we've transferred all this energy into the car, and let's actually put some numbers on so we can have some numbers here. So let's say we have 10 newtons of force to a distance of 10 meters. Nice and easy. Our energy is going to be 100. Okay, 100 joules. However, not all of the energy is going to be transferred usefully. Now our intention when we were pushing this car was to make it move this distance D. So we wanted to make this car move. And so the idea is we wanted to give it kinetic energy. Okay, so the useful energy here was kinetic energy. In this case, it was kinetic energy. Now, the useful energy can change. It depends what you're trying to do. Whatever energy you're actually trying to do or trying to get is the useful energy. So in this case, it was a kinetic energy. But let's say actually that our car didn't, all of that energy was not transferred into kinetic energy, only some of it was. So let's say you have 80 joules of kinetic energy over here, but we know we input 100 joules. There was 100 joules that we pushed into the car because we calculated that earlier. So if the kinetic energy was 80 joules, then we have a gap of 20 joules. So where was that 20 joules? So the idea is this 20 joules might have been from the friction from the car. So it could be thermal energy. It might be some energy transferred to the surroundings. Could be lots of different things, but there's some wasted energy, you might call it. Okay. Energy may be dissipated surroundings, but the main one when you have moving parts is energy, thermal energy to overcome the forces of friction. Okay, so when you have friction between two things that are trying to slide over each other, basically, that means you have some thermal energy. So this is actually not useful energy, and we can actually call it, say straight away, that this is not useful, or you could even say wasted energy. We didn't want to generate this thermal energy, but it was just because there's always friction when we move it that it was generated. Okay, so this is about 20 joules. And we can calculate it because it started off with 100, then we have 80 of kinetic energy. So our not useful energy was 20 joules. Now, if I told you to work out the efficiency, then you should be able to, because you know the formula. So the efficiency is the useful energy that we got out. That was the 80 joules of kinetic energy divided by the total energy that we put in. So that's the 80 joules of kinetic energy plus the 20 joules of wasted energy, or the 100 joules that we put in the first place, right? So that comes from there. And so we can work out here that we should get a total efficiency of 80%. Okay, so you do 80 over 100, you can multiply by 100% to get it in a percentage. Okay, so 80%. And you could do the same thing if you had power ratings instead, if you were to work out how much power. So if you put some times onto here, then we could also work out what the efficiency would be. Now, that does also bring another topic up. Okay, now we want to know how to increase the efficiency, because really and truly, if you've got 100 joules to put in, we don't have unlimited force. You might want to make as much of that force, as much of the energy you put in to be useful energy, kinetic energy that you want to take out. So what we could do is actually lubricate this system here. So whenever you've got moving parts, so let's put a block over here and let's put some ground over here. Now usually there's going to be friction between the block and the ground whenever you try to move it, if this block is actually touching the ground. So let's move it down. Great. And so there's going to be friction over here. So what you can do is add some lubrication between the block and the ground. So again, if we basically lift this up actually a little bit, let's say over here, you put some lubrication between it. So this could be oil or some kind of gel or anything to basically make this slip over the ground more smoothly. That will basically reduce the friction and therefore you reduce the wasted energy. Okay, so this, in this case, a lubrication, this reduces friction or thermal energy that's transferred to overcome that friction or as a result of that friction, and therefore you increase the efficiency. That's one way you can increase the efficiency. Now, another key place where you want to reduce the amount of energy being transferred and wasted essentially, or being dissipated, it is in our homes. So when we heat our homes up, you might have a nice fire in your home, you heat it up, you want to keep your home cool, but actually what might happen is this energy will start to dissipate, it will start to go outside of the home, and this would all be wasted energy. Okay, the minute the heat energy leaves your house, it's wasted because now you're heating up your garden and the street outside and the air outside. It's not really what you want to do, so it's wasted energy. So what we want to do is actually increase the amount of energy that stays within the home and reduce the amount of energy that's wasted and is dissipated outwards. So one way we could do that is through the use of thermal insulation. So if we add an insulating layer around the walls in our house, so for example like this, so we'll label this as thermal insulation. So what does that do now? Now we've got thermal insulation. The idea is that different materials will have different thermal conductivity. So you've seen this kind of property within materials before. So if you think back to specific heat capacity, for example, each material has its own specific heat capacity, and each material will also have its own thermal conductivity. And what this tells us is how much energy, the rate of energy transferred by conduction across that material. So whenever you have a very high thermal conductivity, you're basically going to be able to transfer lots of heat energy away. And vice versa. If you have materials with really low thermal conductivity, then you're not going to be able to transfer that much heat energy away very quickly. The rate of energy transfer is going to be much, much lower. So the idea is with your thermal insulation, you want to use some materials which have really low thermal conductivity. What that will do is keep more of this energy inside, and it will slow down the rate that this energy is dissipated outwards across those walls into the air outside. Okay, and another key thing, as you might actually be able to guess here, is to do with the thickness of the walls. So when you have a thicker wall, so if let's draw a house again, and let's say on this side of the house you've got a really thick wall, so that's quite exaggerated, but you get the idea, and over here you've got a really thin wall. Now here, the thickness of the wall, the thicker the wall is, the lower the thermal conductivity you'll get. And again, this is really important because if you want to keep this heat energy inside of your house, you want to reduce the rate of energy transfer, then you make this wall as thick as possible, and it's going to have a really hard time the energy transferring away from the wall into the air outside, and it's going to take much, much longer to do that. So your house will stay warmer for longer. So again, that's another example of actually reducing unwanted energy transfers. Okay, so that is almost it for energy. The last thing we're going to look at is renewable and non-renewable energy resources. So what I'm going to do here is actually do just a little table, and we're going to list out some renewable energy resources and some non-renewable ones. But first of all, we need to know what that means. So renewable energy resources are energy resources which we can use, but they will be regenerated, they'll come back, and basically they're not finite. Non-renewable is basically the opposite. They are finite energy resources, and one day we're going to run out of them, and some of them might run out quite soon. And so let's actually go through a few examples. So let's take a look at the first one. The most common one that you might come across is a non-renewable is fossil fuels. So these are things like coal or natural gas or oil. These are all non-renewable energy resources because they take so long to regenerate, so long to come back, millions of years, that basically we're going to run out of them. Okay, so they're non-renewable, but they are a main energy resource that we do use a lot, and they are pretty available to us. The next one is a nuclear fuel. Now, nuclear fuel is, again, another example of a non-renewable energy resource, and the reason for that is nuclear fuel requires nuclear material, and again, that is non-renewable, there's a finite amount of nuclear material in the earth that we can actually find. The next one is biofuel. Now, biofuel is actually a renewable energy resource, and the reason for that is basically made from crops and things like that. So you can grow these crops. Once you cut them down, make it into biofuel, you get seeds, and you can grow the crops again every year. So you'll never, in theory, run out of biofuel. You also have wind. So wind is an example of renewable resource because wind, again, we don't have a finite amount of it. Every day we get wind, mostly somewhere in the world. Next one you have is hydroelectricity. So hydroelectricity, again, is an example of a renewable energy resource because essentially it comes from water. So because we don't have a finite amount of water in the world, then we call it renewable. Or we do technically have a finite amount of water, but we don't actually use up the water when we do hydroelectricity. The next one is geothermal energy. So again, that is a renewable one because it's naturally occurring. This is basically from things like volcanic activity. You might have hot water jets underground, and so you can actually harness that energy. It's renewable because these kind of things, they spring up wherever, and basically we just harness that energy once they're being used. They're kind of in certain places around the world, and so that's geothermal energy. The next one then is tidal energy. So tidal energy is again a renewable energy resource. It's, as the name suggests, energy from the tides or from water waves. Basically you can put out machinery into the sea, and it can generate electricity from those tides. And again, it's renewable because you always get tides and you don't use up the tides when you actually generate this electricity. And the next one is the sun or solar energy. Again, it's a very important energy resource, and the idea with the sun is it's renewable because the sun, obviously, it's always there in the daytime, and so we can harness that energy, and it's not a finite resource that is on earth. Okay, so we say it's renewable. Now the thing is, what are these energy resources all used for? Well, we've got kind of three main factors. You can use it for transport. So if you think back to cars and the fuel that you put in cars, you need energy resources for that. So it might be well, most of the time it's petrol or gasoline, and that's from these fossil fuels. Another one is electricity generation. So to actually generate electricity, you need some fuel to do that. As you could have coal-fired power stations, or as we mentioned, some of the other ones as well, solar power, hydroelectric, they can all generate electricity as well. And heating, so just direct heating. So you might burn coal in a coal, you might put coal in your fire, for example, or things like that. Those would also be okay. So we talked about the fact that these are non-renewables, but non-renewables do also have some other things connected to them which make them not so great to use. So not only the fact that they're going to actually run out, but also particularly if you look at fossil fuels, they generate some harmful emissions, so such as CO2 or even sulfur dioxide as well. And CO2 is bad because it causes what we call the greenhouse effect, as I'm sure most of you will have heard of by now. Greenhouse effect basically traps heat within our atmosphere and causes the Earth's temperature to rise. And sulfur dioxide is what causes acid rain, and this can damage habitats or things like that. And the last thing that we want to actually discuss is the idea of electricity generation and patterns of electricity usage. So essentially, you might have a demand for energy within your country or even within the world actually, but the idea is that that demand won't be consistent throughout the day. So it won't look like this. If this was demand on the y-axis and time on the x-axis, then if you were to draw it out like this, you would maybe want to see a nice straight line. Therefore, you know how much demand you need at all times, and you can power on your power stations to meet that demand. Fortunately, you don't see this, so it is a bit more complicated. Instead, you might see something like this. As the idea here is you might have a couple of peaks and then some troughs in the middle. And this is linked with the time of day. So maybe at sort of 6 a.m., depending when you wake up, maybe 8 a.m. is maybe more accurate. But this is when everybody wakes up. And when everybody wakes up, the energy resource requirements are much higher. The demand is much higher. Everyone's getting up. They may be putting on their radios. They're making their breakfast. They're making their tea. They're using water. All of this stuff is energy intensive and it requires energy. And so the demand spikes at this stage. Then everyone starts to go to school, goes to work, and the demand drops off. Then again in the evening, let's say maybe 6 p.m., everyone is back from work. It's about dinner time, tea time, whatever you want to call it. At this stage, the demand again goes up. Everyone's cooking, puts their heating on, puts their TVs on, starts to relax, and so the demand is again going to spike there. And the idea is that if you are planning to meet this demand, then you need to actually be aware of these trends in energy usage. Okay, so over here you're going to actually try to generate more energy, and over here less energy. And so in this case, you can use things like stores of energy, so batteries or things like that, which actually store energy up, generate electricity, store it up. When you need more of it, you use it in these peaks, and then you use less in these troughs. Okay, so that's the general idea of patterns of energy usage, and that is energy done.